The other one as well is I hate this I hate this fact. I think this fact is really dumb. So did you know that 53% of the population of America is female? Australia's close to 50-50. It was just an interesting thing. It's like you would sort of expect. So you sort of expect on average that there is about, in a population, there should be about 50% male, 50% female. So when you see, when I first saw that 53% female in America, I thought to myself, that's actually a pretty big swing. Now, the problem is when I first looked at that was a while ago, and these statistics change year to year. So I don't even think that that's still the case. That's why I think this is actually a really bad fact. But I couldn't find any good facts for 53. I tried to look up 1953 and I couldn't find anything. So yeah, it does. The other reason that I do put this up is because it does give me a chance to talk about difference. So the different percentages. So obviously, most developed countries are close to 50-50, but there are some countries that are not anywhere near 50-50. So if you look at can you search the current one? I don't know. I could, yeah. I don't know what the current one is. The problem is that there's a lot of different websites, and they probably give me different values. So, but I think it used to be about 53%. And so there are a lot of reasons why different countries have different amounts, percentages. If you look at the big one that they always talk about is, of course, China. Now, China only recently banned its one-child policy. So it used to have a one-child policy, which means if you had more than one child, then I don't know what would happen. You would get fined, that child might be taken away. So what they would do is they would say, well, especially in rural areas. If you're in rural areas and you've got yourself a farm, and you're lucky enough to have a baby, you're going to want to make sure that on your farm, then you're going to have a son, because if you've got a son, then you've got someone who can, who's a strong person who can come out and help you in the field, like do stuff. In theory, they didn't want to have a female child because then female baby, she's going to grow up and she's not going to be as strong. Saying that though, I still think they would be strong enough, but whatever. So what they would do is that, they would prefer to have a male baby. So therefore, that actually ended up skewing the results. So in rural China, there ended up being something like 60 or 70% male, and it was really difficult for males in rural China to get to find wives or get girlfriends. So it's actually still a problem today, because obviously this is a generational thing. It's going to take a couple of generations before that sort of changes. So if you were to look at the percentage of males to females in China, I reckon it would probably about maybe 55% males. Again, I don't know the exact statistics. It could be worth looking it up. But yeah, it's just another way. It's an interesting way you can sort of look at the different politics of the world, is by just looking at this simple little statistic: how many males to females? Because we know there should be 50-50. So if it's skewed, then why? As for America, why is it 53%, or why was it 53%? I'm not sure. There must be some kind of pressure that created that, but I don't know what it could be. All right, so let's look at lesson 53, linear programming. We'll be able to use the corner point principle to evaluate an objective function. Wow, there's a lot of new words here. Corner point principle, we've never studied before. But, so hold on, before we move on, Adri said, isn't it dependent on the mother or father? There is actually some, you started this, Adri, so I'm going down this rabbit hole. There is actually some, genetically it's 50-50. However, there are some evolutionary pressures which I think encourage, in times of, I think it's in times of like strife, you know, in times of where there's a biological issues, I think females are preferred over males, I think. So if you've got like, if you've got if there's a drought or something, and so therefore all the animals in a particular region aren't getting enough water, I think what tends to happen is you end up producing more like females than males. Like I think something genetically happens. That's another interesting thing, but I'm not actually 100% sure. We can never remember how it works exactly. I think that's how it works roughly. And so, and then when times are good, you end up producing more males. I think because like if you produce a female genetically, it's like if you produce a female genetically, you are almost guaranteed to pass your genes on because that. Whereas if you produce a male, then you're not as guaranteed to pass your genes on. So that's why. And yeah, sure, it does depend on X and Y parameters, but there's something enough. That's a different sort of way to look at it. Is again, but that's more got to do with the animal kingdom, not necessarily to do with human beings, but it does sort of occur in human beings too. In like war-torn countries and stuff, you're more likely to have female children than male children, I think. But again, don't quote me on any of this. Do your own research because again, when it comes to history and politics and stuff like that, not necessarily the greatest at it, but it's interesting. Okay, so the corner point principle is the principle that we haven't talked about yet. The corner point principle just is just essentially finding, and we'll talk about it, but I'll quickly give you guys, it's like if you have that XY graph, the corner points are these corners. And we can find those corners using simultaneous equations. So that's what we're going to be talking about today. Part of today's going to be simultaneous equations. And the other word that's new here is the word objective function. Now, an objective function is a word that you guys have not seen before. But what we can sort of do is we can sort of look at this word and guess what it might be about. Can someone tell me what is an objective? If I'd say, oh, the objective is this, what does that mean? What is an objective function? Well, what is an objective? Sorry, not objective function. It's a goal or an aim. Thank you. Exactly. So what we're going to do is we're going to look at what that objective function means. And essentially it is a goal. It is what you're aiming to try to achieve. So how can you, an objective function is going to be a way that we can, it can be an aim, it can be a goal that we're trying to achieve, and we're going to look at how is the best way to achieve that goal. And so we're going to, and so at the moment, those two words, the corner point principle and the objective function, seem to be a bit disparate, a bit different. But we're going to talk about how you can use them. Before we do that, the last time I had you guys, we talked about the feasible region. Now, the feasible region is, of course, a region that is defined as a specific thing, rather than it's sort of like taking two inequalities. It's sort of taking two inequalities. So instead of taking one, we take two. And so, for example, what we did for something like, what you could do for an inequality is you could just be like, oh, well, you could have one line that goes like this, and you could have one line that goes like this, and your feasible region may be the actual, just do this. Your feasible region might be this region here, and it's a region enclosed by two or more lines. So far we've been doing just one line, but now we're doing two or more. You could even have three lines. You could have another line here that comes down like this. And yeah, so you could actually bind your feasible region to three lines. And that's what a feasible region is. I will point out that feasible region has 1, 2, 3, for, whoops, sorry, because I've got this line down here, whoopsies. Crap, sorry. Oh. That feasible region has 1, 2, 3, 4, 5 corners to it. And we're going to talk about what's significant about those corners. But yeah, that's what a feasible region is. So what we're going to do today is we're going to talk about, well, how can we use that feasible region? What does it mean? And how can we sort of explore these corners? How can we sort of use this more than just like, oh, let's draw some inequalities? So let's explore it. We're going to start off with an objective function. An objective function is a quantity you want to make as large or small as possible. The limits on this function are your constraints. So this is gonna make a little bit more sense once we start to work on it. But yeah, the maximum and minimum values on an objective function are found at the corners of the feasible region. That is the corner point principle. Ultimately, I probably should have put this on a different slide, but that's okay. So this is what we would refer to as the corner point principle. And therefore, and the other one as well is you only included points, not dotted lines count. Now we're going to go through a big example on this, but I'm going to give you guys a second to copy this down. And then what we'll do is I'll talk about briefly what that might mean. Okay. I'm going to start talking about it down the bottom. I'm going to use sort of Paul Layui as an example, but don't worry, I'm not going to actually use her specifically. But what I'm going to do is I'm going to say this. Imagine that you're working at imagine that you're the owner of a McDonald's store. Okay, cool. You're in the owner of a McDonald's store, and it gets to, I don't know, say Friday night, and you know that you've got to have you've got to run a service on Friday night because you've got to try and make some money, so you've got to sell some burgers. But here's the problem, right? You know it's going to cost you money to run that store. You know that it's going to cost you a certain amount of money to run the store. So why is it going to cost you money? But it's going to cost you money for stock and stuff. But let's ignore that for a second. Let's just talk about the employees. Let's just pretend that you've got two types of employees. Let's just pretend you've got M, which we're going to call managers, and we've got I don't know, we've got T, which is we're going to call team members. Now, if we're going to think about this, a manager of they're probably going to be like an 18-year-old, 19-year-old kid that's thinks that they're top shit because they're like, oh, I'm a manager, so I therefore can boss people around, even though I'm only just now old enough for my voice to break, and I've got a couple of stubbles on my chin that I'm referring to as a beard, even though they're barely there. That's, a manager, he's going to get paid, we're going to say, or she is going to get paid $18. We're going to say a team member, well, they're, pretty cheap. So we're going to call them, we're going to say that they get paid $14. So what you could do is you could find out, well, what's the cost of multiplex? Because no. Okay, so let's just say that you are now the owner of the shop and you want to run. You could then say that the cost of running the shop for that particular night, for that particular Friday night, is going to cost you 18M plus 14T. Okay, because if you've got, and then you could use that to figure, well, this becomes what we will refer to as an objective function. You want to keep this function. If you're the manager, you want to keep your costs. You want to keep your costs low. Okay. You want to keep your costs as small as possible, because that will maximize your profits. So this is what you would refer to as an objective function. If you were to run your store with 10 managers, it will cost you $180. If you were to run your store with 10 team members, it would cost you $140. If you were to run your store with no team members and no managers, it would be the cheapest. It would be $0 to run your store. But here's the catch, right? And there is a catch. That's this, right? The objective function doesn't come by itself. It usually comes with things like constraints, okay? And that's the constraints of what make it a linear graph, and the constraints of what makes it a linear inequality problem. So what are some possible constraints? Well, let's think, like, we could just sort of start to go through some of these possible constraints. Like, the first thing that I can tell is, you know, you can't have 0 people working in the store, right? If you have 0 people working in the store, then it's not going to work, right? You can't, like, and you have to have more than one person in the store, because if you have like one person in the store, then yeah, it's not going to work. So let's just say the smallest amount of people that you can have in a store is 2. So what you could do is you could write M plus T must be greater than or equal to 2. This here, that's a constraint. That says that, yeah, even though it would be the cheapest way that you could have your objective function is to have 0 managers and 0 team members, if you had, like, you know, that wouldn't work anymore, because now you're saying that you have to have more than 2. And so that's what we refer to as a constraint. That constrains this function. And so therefore you could then start to say, well, then is it cheaper to have, is it cheaper to have 2 managers and 0 team members, or 2 team members and 0 managers, or 1 manager and 1 team member? Which of those is the cheaper option? Then we could start to add more constraints. So for example, for me, a constraint might be that you have to have more than 1 manager. You can't just open, you have to have more than or equal to 1 manager. That might be another constraint. For me, that makes sense as a constraint, because, for example, well, you need someone responsible to open the store up, to unlock the doors. You need someone responsible to, you know, to make sure everyone turns up on time. So you need to have more than 1 manager. And in fact, you might even want to start to say is, you don't want to have 1 manager and like 10 team members, because then that's going to be a bit out of control. So I might even say something like, for every for every 4 team members, you need to have 1 manager. So you could say your managers if you take your team members and divide them by 4, your managers need to be more than your team members divided by 4. So if your team, if you've got 5 team members, then you need to have 2 managers. If you've got like 4 team members, you can have, we've got like greater than or equal to. So this is just, yeah, and I'm not going to do this question. What I'm trying to do is I'm trying to show you where this information comes from. And I'm also trying to give you guys a literal example, like an example, so you guys can see why these constraints come up. And so I'm going to stop here, but you can see now we've actually got a fair bit of information. We've got 3 different constraints. You can actually have somewhere, you can have 4, 5, 6 constraints in one question. You've got one objective function. We know for this objective function, we want to minimize it. There are other objective functions that you might want to maximize. You might have money is always the easiest one to maximize. So let's pretend that you run a dress shop and you make dresses, and you've got like different material. You've got leather, and you've got leather material, and you've got like this blue velvet material. You want to say, well, I can make bags which get sold for this much, or I can make dresses that get sold for this much. You know, what's the best way that I can what's the best way that I can maximize my profit? So that's a different way to go about it. Instead of minimizing your objective function, you might want to maximize the objective function. So these are some examples here down the bottom, but yeah, I just wanted to give you guys just a rough idea of what the point of an objective function is and what do these constraints mean. Now, let's now talk about, let's now do a little bit of an example so I can show you guys sort of what we might do in a question like this. So what I'm going to ask you guys to do is I'm going to ask you guys to jot down a basic XY plane that just the first quadrant though, from 0 to 10. And then what we're going to do is we're going to draw at the feasible region like we did last week. And then what we're going to try and do is we're going to try and crack into this objective function and give it a try. So I'm going to give you guys a second to try that. So the funny story about me with managers, while you copy this down, this is not useful, is that I remember when I was, I think I was 19, and I was, you know, I was working at Domino's Pizza, so I was delivery boy, that was my thing. And I remember that they started to say, hey, Matt, would you like to work on Sundays? You could do the open shift. I was like, all right, sure. Because for me, the open shift sounded, 1, it was pretty easy. 2, it meant that I had the whole afternoon to myself. So I would get up and start working at like, I think the store officially opened at like 10. No, the store opened at 10, but we didn't start serving till 11, I don't think. And so, and I would finish at 2 or 3. So it ended up with like a 5-hour shift. So I was like, all right, sure. But the funny part of it was that they needed to get a manager on, because like I was just delivering pizzas. They needed a manager to sort of to make all the food and like prep food and stuff like that. I'm like, okay, sure. The manager they got on was this was a woman called Tanya. And the funny part about Tanya is that Tanya was about, I think from memory, 2, maybe 3 years younger than me. So she was, so it was kind of funny that she was my boss, but she was my boss, and yet I was 19 and she was like 16, 17 or something. And I was like, and she, of course, because we were good friends, we were okay friends. Like we didn't hate each other, but we weren't really friends. But we liked working with each other, and I respected it. But she would still always get a kick out of, I'm bossing you around, and I'm like still in high school, and I'm like, whatever. I didn't care. It didn't bother me as long as we got the job done. And she was really like efficient at getting the job done, so can't complain about that. All right, so let's grab a look at let's grab a look at this question here. So here we've got 4 functions and 4 inequations, and then we've got an objective function. So how do we deal with this? Well, first we're going to plot the easy ones. So x must be greater than 0. That just means that if I was to draw a line down here, it just means there can't be any of these negative values. And y must be greater than 0. Again, just means there can't be any of these negative values. So that's why we only draw the positive and negative sections. Then we've got 2 functions here. X plus y must be less than or equal to 8. And 3x plus 5y must be less than or equal to 30. So let's try and do this. I'm going to start with the first one. I'm going to do maybe in purple. So x plus y must be less than or equal to 8. How do I plot that? Well, what I do is I refer to that as x plus y equals 8. Okay, so we're going to try and plot that. How do I plot that? Well, the easiest way to plot that is because the x and the y are on the same side, I find the best way to plot that is to plot it by intercept method. So what I do is I say let x equals 0, so then that gives me y equals 8. So our first point is 0, 8. And then I say let x equals 0, no, let y equals 0. That's going to be x equals 8, so that's going to give me 8, 0. So that gives me 2 points. One here at 0, 8, and one here at 8, 0. So because I've got 2 points now, I can use that to draw a line. And because it's less than or equal to, I can draw a solid line. The last bit I've got to do is I've got to figure out, well, which side is the shaded side? Well, to do that, again, I like to choose 0, 0. The 0, 0, which is this point down the bottom corner here. If I substitute 0, is 0 plus 0 greater than 8? The answer is 0 greater than 8? No, it's not. 0, actually, sorry, do that the other way around. Is 8 greater than 0? Yes, it is. So therefore, that region, the bottom corner, is the good region. We care about that region. So I'm going to cross out this region at the top. Because 0, 0, 0 plus 0 is less than 8. That is correct. Okay. So now I've got one line. Let's see if I can get a different line. This different line here is, I'm going to do that maybe in blue. 3x plus 5y is less than or equal to 30. Guess what? It's the same logic here. I'm going to try 3x plus 5y equals 30. And then because x and y are on the same side, I'm going to do the same technique. Let x equals 0, 5y equals 30, y equals 6. So that means I've got one point here at 0, 6. The other one, let y equal 0. That's going to give us 3x equals 30, which is going to give me x equals 10. So therefore, that gives me 10, 0. So I'm going to plot those two. So I've got one here at 0, 6, and one here at 10, oops, wrong way, 0, 6, and 10, 0. So down here. So I've got two there. I'm now going to join both of those up. And it's less than or equal to, so that means you're going to draw a solid line. And so that means that, and now the last thing is to check, well, which side is the good side. So we're going to do that by going substitute 0, 0 in. 3 times 0 plus 5 times 0 is less than or equal to 30. What the answer is 0 is less than or equal to 30. Yes, it is. So therefore, that's on the good side. So we want to make sure the other side's crossed out. So we're going to cross that out like so. And what that does is that then creates this feasible region. And we'll label that by going like this. I'm just going to label it up here. Now, unlike in the past, we're actually not quite done yet. And this is the part that takes up a little bit more time. Now, we've got an objective function. Our objective function here, and I'm going to start now working in red, is p equals 2x plus 3y. Now, we want to try and maximize, we want to try and like use this objective function. So I'm just going to show you how you might use it and not necessarily maximize or minimize it, because I haven't written down what you need to do in this graph. So I'm going to show you how you might do that for this particular one. And then what we'll do is I'll give you guys maybe, I think I've been talking to you guys for 48 minutes, so I might as well give you guys some time to start working on Torch after that. But yeah. So the first part to talk about this is to now talk about the corner points. There are, in this question, there's 4 corners. 1, 2, 3, 4. These are the 4 corners of the feasible region. Sometimes you'll have 5, sometimes you may only have 3. Now each of those corners has coordinates. Obviously this one on the bottom is 0, 0. This one here is 0, 6. Yeah, but what about 0, 8? Well, that's not on the corner of our feasible region. This one here is 8, 0, but there is one that's going to be a bit more of a challenge, which is this one here. Now that one there, from my graph, I can tell is about 5.5, 2.5, 5.5 to 2.5. But you probably want to be more specific when you deal with that type of problem in a real life situation. So how do you deal with that in a real life situation? Well, you need to find that point of intersection. How do you do that? With simultaneous equations. Now I'm going to rub off, actually I'm going to try and fit this in at the top. So just forgive me though, but I haven't got much space here, so just be aware of that. So we've got x plus y equals 8, and we've got 3x plus 5y equals 30. We're going to try and find out how these two things are equal. The best way that I can think about doing this is to go with the elimination method. So therefore what I'm going to do, how am I going to eliminate these? I'm going to write this one here, 5x. What was it? Plus 3y. I'm going to take this one here and we go, well, how do I eliminate it? I'm going to go turn that one into 3x or negative 3x, so multiply by negative 3. Negative 3x minus 3y equals negative 24. If you don't remember how to do this, what I'm doing is I'm multiplying each of those terms by negative 3. Because when I add these two equations together, what I'm going to get is I'm going to get this negative 3x plus 5x. That's going to give me 2x. But negative 3 plus 3 is going to give me 0y. And then negative 24 plus 30 is going to give me negative 6. No, 6, just positive 6. Oops. So therefore, x equals 3. And if I substitute x equals 3 into this top equation here, we'll do that over here. 3 plus y equals 8. Y equals 5. So that means this point here, hold on a sec, I feel like I made a mistake. Let me just check. Oh crap, that's where I made a mistake. Whoopsies. I got my I'm sorry guys, I got my terms wrong. See, I've gone 5x plus 3y. It's not 5x plus 3y, it's 3x plus 5y. I got my numbers confused. I apologize. Okay, so let me try that again. Let me try that again. Hopefully, hopefully this makes sense to you guys. So if I try this again, so 3x plus 5y. Now the numbers should actually be pretty similar because I just got them jumbled up. But if you watch, in this case, 3x plus 3x equals 0. When you add these together, plus 2y is equal to 6. So y equals 3. You substitute y equals 3 into the top equation. Substitute y equals 3. Then what that'll give you is x plus 3 equals 8, x equals 5. So therefore our corner point should be at 5, 3. Now, if you look at this, here's 5, here's 3. So this point here is our corner point. So I kind of missed it a little bit. When I drew this, I didn't do it very well. So that gives us the coordinate 5, 3. So now we've got 1, 2, 3, 4 corner points, and we've actually labeled each of them. And at this point, you could now, evaluate the objective function. How do you evaluate the objective function? Well, let's do P at all 3 points. So we're going to start with the easy one, this bottom left-hand corner. And trust me, guys, I know that at this point you're probably like, oh my God, I'm so tired of this same question. We've been working on it for 5 minutes. Yeah, trust me, I know we've been working on this question for a while, but this is the home stretch. So we're going to evaluate P. So the objective function here, let's start with 0, 0. That's this corner down the bottom left. That means that P equals 2 times 0 plus 3 times 0. P equals 0. Done. Let's evaluate it for 0, 6. So for 0, 6, we're going to have P equals 2 times 0 plus 3 times 6. That means P is going to be 18. For 5, 3, 5, 3, we're going to have P equals 2 times 5 plus 3 times 3. 2 times 5 is 10, plus 3 times 3 is 19. And for the last one, 8, 0, we're going to have 2 times 8 plus 3 times 0. 2 times 8 is 16, plus 0 is 0. So, and then this becomes our objective function evaluated. Now, this question doesn't ask us to maximize or minimize P, but we can sort of tell if we wanted to maximize P, if we want P to be the largest it possibly could be, then 5, 3 would be the best corner to use. Let's just say if X, again, if going back to our previous example, if X was like the amount that you had to, of team members and Y was the amount of managers, then you would want 5 team members and 3 managers or something to make sure that you got the most amount of money while keeping the store running. If instead you wanted to minimize it, then the smallest value is 0, 0, because it is the smallest value for P. So now that we've finished this whole question, let's just talk about the different parts that went into going to do this question. Now, it's actually very rare that you actually have to do all of these steps in one question, but I have seen questions like this, but I just want to show you guys the steps. The first thing that we did was we plotted these two, we plotted all the equations. That was the first step. Now that in itself, you guys need to get as much practice as you can of plotting those things. The second step was labeling the corners. And for 3 of those corners, it was really easy. But for one of them, it was a little bit more of a challenge. We actually had to do some simultaneous equations. The last step was to then evaluate P. So this, and that was putting the equation in. And of course, when you're plotting inequalities, making sure you know which side is shaded is really important. And hopefully now you guys can start to see why in the previous lessons I spent so much time saying don't shade the feasible region, because you can see now that it's getting a bit crazy, a bit hectic with all these lines going over it. So therefore, making sure that it's not shaded makes it a bit easier for us to see where the region is. Now, I could go through some extra stuff here with finding the corner points and stuff like that and talking about constraints, but I feel like that whole section here took a very, very long time and was a bit laborious. So what I want to do is I would like to give you guys instead some time today to work on the topic. Let me just share with you guys what I think you should be working on. So here's 12G. So if you look at 12G, 12G is the same sort of questions that you guys, it's similar to what we just did. Okay. If we go have a look at the example for 12G, what they do for you guys is they give you guys the graph already done. And so all you've got to do is you don't actually have to draw these lines. The reason that I spent time drawing these lines is so that you guys can, get a bit familiar. If you actually look at this example here, it's actually got we already did this question just then. It's just got the same thing. So, but they already give you guys the pre-sketch graph, whereas we actually tried to explore it ourselves. And so therefore they then did it, and then they found that the maximum value is here. So they were looking for a maximum, find the maximum value of the objective function. Here's another one, but this one they want to find the minimum value. So you've got 1, 2, 3 corners. So therefore they substitute those 3 corners in, and then they found the smallest one happens to be 0, 9. So you guys, for this, is that you've already been given a feasible region. So you don't need to draw these lines like we did. You don't even need to calculate what these intersections are. You just need to substitute them in. So that's 12G, questions 1, 2, 3, 4, 5, and 6.